So let's look at Boyle's law. Okay, so for this experiment, we are investigating the correlation of volume and pressure at a constant temperature. Okay, so that's Boyle and the Mariotte law. Okay, so for Boyle and Mariotte's law, let's look at what Boyle and Mariotte's law says. Okay, so Boyle's law states that the absolute pressure exerted by a given mass of an ideal gas is inversely proportional to the volume it occupies. If the temperature and the amount of gas remain unchanged within a closed system. Okay, so this is Boyle's law. Now we have to use this Boyle's law equation, right, to be able to generate the equation that we'll use for this experiment. Now in the part 1 of this video is how the experiment is performed. Okay, now let's look at this. It says the absolute pressure exerted by a given mass of an ideal gas is inversely proportional to its volume. Okay, so we can say that it says that P, right, P being our pressure, is inversely proportional to the volume. So of an ideal gas, right, if the temperature and the amount of gas remains unchanged. So we can call this equation 1. Okay, we are not done. We'll come to the table. Okay, so with this, the theory, we are on the theory. So with this, we can continue by saying that if this is proportional to this, right, then we can say that this is true. This is true because we want to take the proportionality and then introduce an equal to sign. Okay, if we do this, we can also say that this is also true. Now this constant, right, this constant, we can call this R, the universal gas constant. So we can call this R. But mind you, coming back to the law, it says that if the temperature of the amount of gas, if the temperature and the amount of gas remains unchanged. So with that, we can say that if we say N, if N is the amount of gas, right, or amount of substance, N is the amount of substance, right, and then we said that our R, our K can be equal to R. right, equals to the universal gas constant. Okay, and then T, let me just write it here. T is our temperature at a constant temperature, right? So we are just continuing with this. We looked at the first part of the law and then we got this, right? Let's call this equation 2. Then we are looking at the second part of the law and then temperature. Okay, so then we can also see that in trying to add this and then this to this, because it says that an ideal gas, now we know that the ideal gas formula is given by PV equals to nRT. Okay, so within the closed system, so the ideal gas, okay, a given mass of gas is our N. You see, we call it the amount of substance. So that substance is our gas, okay, at a constant temperature, our T, and then this our constant, okay, our proportionality constant that we introduced. So our proportionality constant becomes our universal gas constant. Okay, so from this equation, right, from this equation, we are supposed to find R, our universal gas constant. And then we know this, our R, universal gas constant value to be 8.314 Newton meter dot Kelvin per Kelvin dot mole per mole. Okay, so we are interested in finding this value. Okay, now how do we do that? In the part 1 of the video, we looked at how the experiment is performed. Okay, so let's look at how the table will look like. Now our table, we are expecting to get a table like this. Okay, our first quantity can be any of this, the L, the change in L, or this. So let's use the L in millimeters, right? Then our next value, or our next quantity, is supposed to be our change in height, change in h or height, which is also in mm. Then our volume in milliliters. Okay, our volume should be in milliliters. Then our pressure, you see, and then our pressure in kilopascal. Then the inverse of the pressure. Okay, now how do we complete the table? You realize that in the part 1 of the video, we only got our L and then our H values. Okay, so to get this and this value, this and this values, right, there's this formula. Okay, we use this formula. So we all know that volume is our pi, and then this should be our diameter divided by 2. So this is the radius, so pi r squared. Okay, pi r squared. Then we add our L to it. Okay, so finally the value of the L that we had in this section, we are using this equation here to find V. So when we take the first value here, we insert it here, then we find the first value here. We take the second value, insert it here, and then we find the second value. So we use this equation to find V. Then we come here. We're also using this equation to find all the P values. Okay, so this P and this V. Okay. Now, our PA is our atmospheric pressure, which is giving us our PA is giving us 100.3 kilopascal. So that's the value you use here. Then we take the first value here, insert it here, times this, then we write it here, right? So we just insert the values that we had here. This is a constant, then we can find all the values here. Now this is just an inverse of this. Okay, now in doing that we are expected to get two graphs. So we are plotting two graphs. Okay, one graph that looks like this. The first graph that we'll be plotting is V on okay, this is the first graph that we'll plot, and then the first graph is supposed to give us a curve which looks like this. So that's the first graph. We are plotting two graphs, mind you. Now our second graph, okay, our second graph is, we will plot this V ml against 1 on P, against 1 on P kilopascal, right? Now the values that you'll be getting might be decimal values. Okay, so we can convert this into 10 raised to the power 3. So you can just convert, you can just use this conversion so that we can be able to plot this. And then after doing that, we will have a line that looks like this. Okay, so we are plotting two graphs. One that looks like this is a curve, and then the one that looks also like this, that is for P. So this should be V against, this should be V against 1 on P, and then this should be V against P. Okay, now let's move on. Now after doing that, our manual says that the pre-lab questions they gave us here, okay, it says that we should plot two graphs, V against P and then V against inverse of P. And then when we do that, we should find the slope for the second graph only. Then when we find the slope for the second graph, we use the slope to determine R, right? Given in this, R given in this. Okay, so we are interested in finding R. Okay, right? We are interested in finding R giving N as this. Giving N as this. Okay, so let's continue. Now, to find the slope for the second graph, after finding the slope, where the slope will be found as our change in V on V, ml is ml, on change in 1 on P times 10 raised to the power 3 kilopascal. After finding the slope, after finding your answer for the slope, what we do next is we come and quote this equation, PV equals to nRT, okay, PV equals to nRT. Okay, now let's try and then find the x and y components from this expression. Okay, let's try and find the x and y components from this expression. So what we do is that we make V the subject because we are plotting V on the y-axis. So this one becomes nRT on P. Okay, we are using the second graph. So since we are using the second graph, we can say that in factorizing 1 on P out or P out, we will have an expression like this. Okay, so this becomes the expression. This becomes the expression. Mind you, we are plotting this against this. So anything in front of our x component becomes our x, our slope, our gradient. So comparing to this mx plus c, our y component becomes our v, our x component becomes our 1 on p, our m, which is the gradient or the slope, becomes nRT. Okay, and then our intercept becomes 0, so there's no plus anything here, so no intercept. Okay, so the graph is expected to go through the middle. The expected graph, like this, is supposed to go through the middle, the second graph. So we find the slope. Okay, now after finding the slope, we come and equate the value of the slope. So we can say that our slope, we are interested in finding R, the universal gas constant. So our slope becomes nRT. Now they said Boyle's law, P is inversely proportional to V, right, at constant temperature. So the temperature that you used in the lab, okay, is what you use. But please, you make sure you convert the temperature to Kelvin. Okay, you convert the temperature that you used in the lab to Kelvin. Okay, you convert it to Kelvin. Okay, so our n is given as, let's make R the subject first before we put in the values. So we are interested in finding R, so we can just divide this side by this and this, so that R stands alone. So our R now becomes our slope on n and then t. So our R becomes the value of our slope on, they said we should use n, so the value of n is 0.9536. right? And then our T, we are using 273.15 Kelvin. So our T should be in Kelvin. Mind you, don't forget, you convert the temperature to Kelvin, you get this, and then the n value. Then you can find R, the universal gas constant. Okay. Now we can further use this to find the coefficient of cubic compressibility, right? Coefficient of cubic compressibility. Okay, so let's write that one here. Coefficient of cubic compressibility. Now we can say our x naught equals to coefficient of cubic compressibility, which is given as V naught on the differential or the change in, where we kept our T and then n constant, right? So if you are asked to find coefficient of cubic compressibility for the Mariotte and the Boyle's law, you have to use this expression to find x naught, which is our coefficient of cubic compressibility. Thank you very much. If you have any further questions, you can contact me on, you can WhatsApp me on this number. Thank you.